Okay, welcome everyone to our statistics lesson. Today is going to be a neat exercise and just looking at the relationships in our data. So between SDG scores, between the indicators themselves. So let's navigate from the home page of our course website to our stats pane. And quickly, I'll go over just the topics of today. We'll go through the code just on the website here as an overview, and then we'll take a deep dive in RStudio where I share my screen and we talk about the functions and we get to run the code together. So this will just be an overview of the topics and some of just the theory behind the statistics, and then we'll jump into RStudio together. So today's topics are linear regression. So how can we tell if two variables in our data set are correlated with each other? Is there a relationship between two variables? Relatively simple question, and we could answer it with some simple code. The correlation matrix, how can we determine correlation between all SDG scores more efficiently than by employing or visualizing linear regression for every pair of SDG scores? Can we see broader patterns? So with linear regression, we're looking at pairs. We're looking are SDG 1, no poverty, and SDG 3, good health and well-being. Are those related? But with the correlation matrix, we could look at our whole data frame, or all of the SDG scores, and every pair just in one diagram. So everything from our linear regression, just as a big picture where maybe we can see broad patterns between SDG scores and other scores and indicators. So we start, as always, just by loading in our Sustainability Development Report data from 2023 with read CSV in here. Then we clean the names of our columns with the janitor package and clean names function. And we start with a scatter plot, similar to the one that we made yesterday with goal 1 scores on our y-axis and goal 7 scores on our x-axis. And each point is a country. So we have goal 1 of no poverty and goal 7 of renewable energy. And we have each point as a country. So just by looking at this right off the bat, it seems our largest cluster of points tends to be at really high goal 1 scores, right? Like almost close to 100 here. And goal 7 scores of about 75 or just under. That's where a lot of countries fall. But there is a ton of variance where countries lay, right? We have countries with high goal 1 scores here and relatively low goal 1 scores. We have distribution, countries are all over the board here. But our general trend seems to be up and to the right if we look at these points. It is hard to see just like this. So this is where we start employing linear regression to see, can we draw a line through these points to see if there's some sort of direction. So let's draw a line with the geom smooth function in ggplot. And here it is. This line tends to go up and to the right, right? So this actually indicates that there is a relationship. If the line was flat, we would say maybe there's no relationship. But this line going up and to the right through these points indicates that there's a positive correlation. So a positive correlation exists when two variables move in the same direction. This means that as one variable increases, the other variable also tends to increase. Similarly, when one variable decreases, the other variable tends to decrease. Graphically, a positive correlation is represented by a trend with a line sloping upwards from left to right on a scatter plot. So similar to what we see right here. A good example of this, I think, is the more hours you spend studying for an exam, the higher your exam score is likely to be. In this case, studying time and exam score will have a positive correlation. So if you could imagine, studying time was on the y-axis here, maybe in hours. If this was 30 hours, so a long amount of time studying, 60 hours, 90 hours. And then exam scores on the x-axis. This would be low exam scores, and right close to 100 would be high exam scores. We might see the same kind of relationship if each point was a student taking that exam, where we might see a cluster of those students that studied a ton, 90 hours. Maybe this is like a LSAT or something, 90 hours of studying. They're getting these relatively higher exam scores. And then students that spent the lower amount of hours studying will maybe get lower exam scores, be in this kind of bottom left portion of our scatter plot. But of course, there will be outliers to this, right? We all know maybe some folks that can study just a little bit and get a high score. So that might be a point over here in this bottom right portion, where they did a little amount of studying but received a high test score. And then some folks, right, might study a lot but just do poorly on that day of the exam. So there will always be outliers to these relationships, but we just try to measure general trends with them. So we covered a positive correlation. A negative correlation exists when two variables move in opposite directions. So this means that as one variable increases, the other variable tends to decrease and vice versa. So graphically, a negative correlation is represented by a trend line sloping downwards from left to right on a scatter plot. So the opposite of what we see right above in that plot. And a good example of this, I think, is the more days a person exercises per week, the lower their body weight tends to be. So if we had exercise days on a y-axis and body weight on an x, we should see as exercise increases, body weight tends to decrease. So now we can see a line moving up to the right, indicating a positive correlation. Our next question is, can we measure that relationship? Is it a strong positive correlation? Is it a weak positive correlation? And the answer is yes. We can measure with the correlation coefficient. So we use the stat core function here to calculate a correlation coefficient. And here we print it out on the graph, 0.79. So 0.79 indicates a strong positive correlation. So in both negative and positive correlations, the strength of the relationship between variables can vary. The correlation coefficient is a statistical measure that quantifies the strength and direction of a correlation, and it ranges from -1 to 1. So a correlation coefficient of 1 indicates a perfect positive correlation, -1 indicates a perfect negative correlation, and 0 indicates no correlation. So here we have 0.79 out of a potential 1, indicating a strong positive correlation. So let's look at this resource just to learn more about correlation coefficients and how they move. So this is done by the R psychologist. I think it's a really neat education tool. And what it is, so we see here points similar to the scatter plot we have, right? Imagine if each one of these points represented a country with our goal 1 scores and our goal 7 scores on the axes. If the points fell like this on the plot, there'd be a correlation of 0, right? There's no kind of direction in these points. They're kind of spread without any relationship. But as we create a relationship, we can actually, with this tool, drag the points and move them. And as we move this up and to the right, you can see that correlation coefficient changing. So now it's 0.18 out of a potential 1, so still very close to 0. We would still consider this basically no relationship. But the more points that we drag up and to the right, we see our trend line changes, right? To go through those points and follow these. And the more that we drag to this upper right corner, the higher this correlation coefficient is, indicating a stronger positive correlation. And you'll see that number keeps increasing if we keep fitting that trend, right? So if we put some lines or some points down here in this bottom left, our trend line will keep going up and to the right. And now these points are taking some shape, right? And our line is going through them. Now we're at a 0.68, so what's considered to be a relatively strong positive correlation, 0.71. And as we keep fitting this and maybe moving even these kind of outliers here, we get a 0.79 eventually. So it's the same that we see on our scatter plot, right? So a relatively strong positive relationship. And the same thing goes, so if we start going against that relationship, you'll see that correlation coefficient starts to decrease, right? It's heading back towards 0 because these points are kind of having less of a shape, right? And our trend line is fitting through them and becoming more just even and horizontal. So soon enough, right, we'll get back to a 0 correlation coefficient. I can drag points from this top right section down. And now we're back at 0 for here. So this is no relationship again. But now let's create a negative correlation. So if we keep dragging these points down, our trend line tends to go down to the right, and fit these lines, indicating a negative correlation. And it's that negative number is getting closer and closer to -1, right? As I keep moving these points. Same goes for this portion of the graph. If I keep moving these points to fit this down to the right direction, we'll get close to 1, right? So this is -0.7. So relatively strong negative correlation. And eventually, if all of these points fit a perfect line going down to the right, we would be at a correlation of -1, indicating a perfect negative correlation. So as strong as a relationship can get in a negative sense, right? And +1 would be as strong as a relationship can get in a positive sense. So I think that's a useful tool. Please, I encourage you to go to this rpsychologist.com and play with it and drag the points. You can create new points even if you'd like and see how outliers affect the way the trend line looks and that correlation coefficient. Theoretically, the more points, right, the less influence just one point has on the correlation coefficient. So with just a few, right, if we change 3 of 5 points, right, that might have a huge difference. But if we change 20 of 200 points, it might not have that much of a difference. So the number of points becomes really interesting to play with as well. So let's go back now that we learned a little bit about correlation coefficients and talk about the p-value. So we printed our correlation coefficient here, r equals 0.79, our strong positive relationship. We have p-value here is -2.2 e to the 16th. And this is indicating significance. So the p-value is a measure that helps determine the significance of the results obtained from a statistical test. So p-values have been highly criticized in science. It's not a be-all, end-all measurement, but you'll hear them all the time, right? That this is a statistically significant relationship, and that is oftentimes based on a p-value being less than 0.05. So we get a p-value on our graph from the stat-core function of 2.2 e to the -16. So a very small number, extremely close to 0, indicating that this is a statistically significant relationship or less than 0.05. So let's continue now from our p-value indicating statistical significance into the correlation matrix. So we start by just selecting our SDG scores, so not the indicators, just goal 1 score, goal 2 score, so on till we get to 17 from our data frame. So now we have a subset of data frame of just our overall goal scores. We create a matrix, and then we calculate correlations, and we're able to visualize those correlations with ggCorePlot and a correlation matrix. And here's what that looks like. So we have goal 1 score to goal 16 on our y-axis, and goal 2 score to goal 17 on our x-axis. And each of these bubbles represents a correlation coefficient. So the same as we saw here and the same number that we saw on that R Psychologist website. It's a correlation coefficient between the two SDG scores. So just as a glance, we see lots of red, right? And red indicates a positive correlation. And the darker the red, the higher that correlation coefficient is. So the stronger that positive correlation is. As we get to purple, we see the darker the purple, the closer to -1, or the stronger that negative correlation is. And we see some white, right, which indicates just no relationship between those two SDG scores. So let's just take an example. We have in the bottom left, goal 1 and goal 2. So that would be no poverty. And we'll always remind ourselves that SDG 2, right, I believe is 0 hunger. So SDG 2, right, and SDG 1, their scores have a 0.56 positive correlation. So this is just getting into the strong range between 0 and 1. We're at a 0.56. But we do see some darker red circles here, right? So goal 1 and goal 3 is the bubble to the right. And that's a 0.87 out of a potential 1, indicating a really strong positive correlation, right? And the darker the red, again, the stronger that relationship is, or the closer to 1 we are. So that's goal 1 and goal 3. So that would be no poverty and good health and well-being. So that is suggesting goal 1 and goal 3 are very correlated with each other. And as one increases, the other tends to increase. So now let's take a look at a negative correlation. So if we see here and we go to goal 9 on our y-axis and goal 12 on our x-axis, we see a negative 0.83 correlation coefficient, indicating a strong negative correlation with that dark purple. So let's think, goal 9 is innovation, industry, and infrastructure. And goal 12 is responsible consumption. So this is suggesting as innovation, industry, and infrastructure tend to increase, goal 12 or responsible consumption tends to decrease. And I think this is something that we can see throughout our world, right? As we tend to build and increase production, right? That footprint tends to increase, right? And the way we consume becomes more efficient, maybe, and less responsible. So that's what this is suggesting. And the same thing happens with goal 13. We see another row of purple, right? Indicating negative correlations. So let's stay with goal 9 and just look at the relationship between goal 9 and goal 13. So goal 9 are industry, innovation, and infrastructure. And goal 13, climate action, have a negative correlation of 0.76, so relatively strong negative relationship, indicating that as industry, innovation, and infrastructure increases, the SDG score for climate action tends to decrease, right? And we see that again throughout our world, right? As some countries that have tons of infrastructure and tons of development, there tends to not be sustainable infrastructure or infrastructure that doesn't have significant carbon emissions. So this negative correlation is also something that we see, I think, in our world, and that's what this chart suggests. Obviously, these are really complex relationships, and this kind of simplifies it. But I think it does agree with things that we see day to day throughout our world, that climate action and responsible consumption tend to be negatively correlated with things like industry and infrastructure. It is really interesting that our strongest positive correlation looks like it's between goal 3 and goal 9. So again, goal 9 is that industry and innovation, and goal 3 is good health and well-being. And there's this 0.9 positive correlation coefficient, indicating the strongest relationship on this graph. So we see good health and well-being is increasing as innovation, industry, and infrastructure tend to increase, right? So that does make sense as well, right? The more hospitals you build, the more capital there is, maybe the healthier people are. But we have to think about health and its measurements, right? And the indicators in these scores, right? So we're measuring health in only the ways in the indicators, right? So places that are likely to be maybe more economically advantaged have higher scores in this goal 3 section. And that's something that we see and that we can hypothesize and draw other figures to try to explain that relationship more. But this broad correlation matrix that simplifies really complex patterns in our world, I think does a good job at hinting the relationships between things like climate action and innovation and infrastructure, but also good health and well-being and how that might be positively correlated with industry and infrastructure. So this paints an interesting picture, and we'll talk about that in the challenge and even in the code in just a little bit. So now just to recap with one last figure, if we plotted with a scatter plot similar to what we started with, goal 9 on the y-axis and goal 12 on the x-axis, we see this line going down to the right, indicating a negative correlation. And our R here, our correlation coefficient equals negative 0.82, right? So a negative correlation. And that should be the same thing that we see in our correlation matrix, right? So if we go between goal 9 and goal 12, here, we just chatted about it. We see this negative 0.83. So give or take 1 decimal, but that's a good way to think about the correlation matrix. So it's almost like a bunch of scatter plots just lined up in one way where we could see all the pairs of relationships. But that negative 0.83, give or take 1 decimal point, is the same that we see here when we plot a scatter plot of goal 9 and goal 12, with each point being a country, right? We see that downward trend where there seems to be a high concentration of countries with high goal 12 scores, but low goal 9 scores. So good climate action scores, but low scores in industry and innovation. And today's challenge is interesting. It just takes editing the code chunk above this to plot a linear regression of two different SDG scores. And it comes with a few tasks. So make the plot interactive with ggplotly so that you can hover over the points and see the country, as well as the x-axis score and the y-axis score. So some hints here to be able to tell which point is which country. You'll have to add label equals country in the code, and we'll talk about that when I start sharing RStudio. And for this ggplotly function, you'll need to use library to load in the plotly package in the first code check. And then we're just asking you to, in 4 to 6 sentences, come up with a hypothesis for the positive or negative correlation between the two goals. We want you to think about, are there any points that don't follow the trend, so outliers? And which countries are those outliers? And maybe think about why that country might be an outlier to the trend that the rest of the countries follow. So now let's look at RStudio. You can navigate here. And we're in our SDG Analytics and R project. And here we see if we open our files pane, we'll go to that R markdowns folder, and we'll open up our stats.rmd. Let's give this a full screen. So here's our code, right, that mirrors what we see on the website. The libraries we use are tidyverse, as always. We use the here function for reading in our data. And this ggpubr is the package that we use to calculate those correlation coefficients that we talked about. And then as always, library janitor to clean our column names. So let's start here by running this top code chunk, our libraries. Then our next code chunk will be reading in our data with read CSV in here. And now in our environment pane, we could check out our SDR data frame. And we clean our column names, right? So we have spaces in our column names now, but when we use that janitor function, we clean the names. Now when we check out SDR data, every column name is lowercase with underscores. And here's where we generate the scatter plot from our SDR data frame with goal 7 scores on our x-axis, goal 1 scores on our y-axis. We use geoPoint to create a scatter plot, and we just add theme minimal just to get rid of the gray background that we often see with ggplot. And now we go to the linear regression, so drawing a line between the points. And in the code, this is where we use the geom smooth function. So this comes from within ggplot, and we just simply add it to geoPoint, right? So just using geoPoint makes this scatter plot, but just adding this plus sign in geom smooth, followed by a plus with theme minimal, is what gives us that line between the points. And this is our line. Those gray spaces are known as error margins. So they're nice and pretty tight to the line. Sometimes we'll see error margins that are huge, and that makes you take a step back and think about the analysis and think about potential error and just how much margin or range for error there is. Then we think about, okay, positive and negative correlations that we covered just before. And here's where we use the stat core function. So again, we're just building on top of that scatter plot one at a time. We use geom point to create the scatter plot, and then geom smooth is what adds that line. And now the stat core function is what adds that correlation coefficient. We see that negative 0.79 in the p-value that is below 0.05, indicating some statistical significance. And that all comes, yeah, just from this stat core function from that ggpubr package. So remember, if you don't have the ggpubr package, you can install it in the console. Just with install.packages. And in quotes, it would be ggpubr. And now as we go down through the text, we'll get to where we subset. So this was a really important part of making that correlation matrix. So we have this idea, right, of we want to see the relationships between all the scores, but that means that we have to subset our data to just select the columns that are goal scores, right? So SDR data has lots of columns in it. If we check our environment, yeah, it is. There are 666 variables within SDR data. But we only want these columns, just the goal scorers. We're not even interested in the country for this part of the analysis. So we use our pipe function. We're creating a new data frame, SDR scores, from SDR data, and we select only the columns we're interested in. So when we run this code, our SDR scores data frame looks like this. Just the goal scores. So we have 17 columns and 206 rows still. We didn't get rid of any rows. We just selected the columns that we're interested in. And now we create a matrix from the data frame with the as.matrix function. You can see here when you click on it, it's very similar. The only reason we do this is because the correlation function, core here, only takes matrices. It doesn't take data frames in this argument. So we need to make that data frame a matrix, even though it looks similar to us. It's just the way that core function works, that it only takes a matrix and not a data frame. So we named that SDG scores matrix, and now we'll create an object called core, and it's using the core function on our matrix. And there's a few different methods. Ours is the most common, this complete observations. When we do that, we can click on core here. And these are the correlation coefficients. So that's the function that calculates them. And so now we see there's, with goal 1 and goal 1, right, there's a perfect correlation because they're the same. And that happens with goal 2 and goal 3. But we see between goal 1 and goal 2, there's this 0.55 positive correlation. We see that 0.86 positive correlation between goal 1 and goal 3. So this is a data frame of all the correlation coefficients. Run this ggcoreplot function. It needs a few arguments. So the first is our correlation coefficients in matrix format. So that's what we have here, what we saved as core. We use the circle method as just a method of plotting with bubbles instead of squares. Type equals lower. We don't have any repeats. So sometimes you'll see a correlation matrix where there's a repeat, but type equals lower just means that we have just one correlation coefficient for each pair of SDG scores. We want the labels, and we want the label size to be 2. It was a little tricky fitting all of this, so we change our x-axis or our y-axis text to a smaller size, to size 8, and our x-axis text also to size 8 with that element text function. So yeah, again, when I just created this, it took up a lot of room, so I just needed to just make those axis titles smaller. So when we run this, we'll see it looks like this. So a little bit clustered to where what we see on the website. But if we full screen, it will spread out a little bit. And here we have our correlation matrix, right? So we recapped it in the video, but just as a summary on how we made that, we used the ggcoreplot function from the ggcoreplot package. And we used the circle method to plot. If we wanted to, you could look up GG core plot. There's lots of different methods to plot that look pretty neat. I appreciate this one. I like the way that this tends to look. But I'm curious of your opinion and how you like to see a correlation matrix. There's tons of examples if you just Google GG core plot. And we just changed these two lines of code, right, are just about changing the size of these labels of goal 16 score and goal 15, and that just to fit. So now when we go down, our last bit is just recapping, right? And plotting one more scatter plot with a trend line using geom smooth and a correlation coefficient using stat core. And from this, we get a plot that shows a negative correlation between goal 9 and goal 12. So what we want you to do in the challenge is to edit this code chunk above to plot a linear regression of two different SDG scores. So replacing X and Y, right, with the goal scores that you're interested in. Make the plot interactive with ggplotly so you can hover over the points and see the country, right? When we look at this, right, each one of these points is a country, but we don't know which one, right? So if we make the plot interactive, that will be really neat, right? And we could see which countries are which point. And it adds a whole layer to the visualization that becomes really interesting. But to do this, it takes kind of two steps. So you'll have to add label equals country into the aesthetic function. So after your X and your Y with a comma, you'll add label equals country. And then you name the plot and put it into the ggplotly function. So this is an advanced visualization, so please revisit that and see the output and layout of that code. But naming the plot and putting it into the ggplotly function after you've added label equals country inside this AES function here, right after your X and Y axis, you should have an interactive plot. And then in 4 to 6 sentences, we would like you to come up with a hypothesis for the positive or negative correlation between the two goals and hover over the graph and see, are there any points that don't follow the trend? Are there any outliers? And which countries are those outliers? And I'd like you to think about maybe why. What about that country makes it not follow the same trend maybe as the rest of the world, right? So just replacing those SDG scores and doing some critical thinking with your interactive plot is today's challenge with the stat core function.